Okay, so this video is an optional video talking about the meaning of dy dx, which is the derivative of y with respect to x. There's actually a lot to unpack here. So we're going to start with this phrase, the derivative of y with respect to x. So what that's talking about is talking basically about how quickly y is changing with respect to how quickly x is changing. Nice picture here is like I could imagine X is some person with a barrel here, and maybe he's putting a bunch of oranges in his barrel. Here's some oranges. And then we got Y. Y will be a person too. Y has also got their own barrel. And they're putting in some apples. We'll put red for apples. Those are great apples. I am an artist. You know it. All right. So let's say we've got let's make a dy dx. Let's say dy dx is equal to 2. Now we already know, we know what dy dx stands for. It stands for the slope of the tangent line. In this case, the slope is 2 everywhere. We'll talk about what that means graphically, but let's think about what it means in terms with this phrase, the derivative of y with respect to x. What that's saying is it means that for every time x puts an orange in its barrel, y is going to put 2 oranges in its barrel. It's got a rate of change that's twice as fast, right? So the change of y is twice as fast as that of x. So x is going to sit here and put in, x puts in an orange. Like, I'm going to put in an orange. And y sees that and says, well, if you put in an orange, I'm going to put in 2 apples, right? Twice the rate. X will say, well, fine, I'll put in 2 oranges. And y will say, no problem. I'll put in 1, 2, 3, 4 apples. Maybe X gets frustrated and says, fine, I'm going to take away all 3. Oh, that's like all 3. X takes away 1 orange. And Y will take away, guess how many apples? 2 apples. So the rate of change of Y is always twice that of X. Don't mistake that with thinking that there's always going to be twice the amount of apples in that barrel. Like X might have started with this many oranges, and Y maybe only had that many apples. It has to do with the rate of change. So now if X adds 1 more orange, then Y would add 2 more apples. You'll notice this isn't necessarily twice the amount of that. That's because lines like y equals 2x, or y equals 2x plus 7, or y equals 2x plus 18, right? They all have a slope of 2. But you'll notice that doesn't mean the y is always twice as big. Sometimes it's twice as big plus 7, or twice as big plus 18, or something else. So all that it means is that it's got a slope of 2. So dy dx, that's the slope of the line if I had graphed this type of situation, right? You can see this whole idea of y going twice as fast on a graph as well, which I'll show in just a minute. All right, so here I've got the line y equals 2x, which we know has a slope of 2 everywhere. But what I'm going to do for a minute is I'm going to hide that line. And instead, I'm going to show you this red line and that green line. This red line is just a value of y. That green line is just a value of x. And if I move this slider, you'll notice I'm going to move that green line 5 units. So from here to there, right? If I move that green line 5 units, look how far the red line moved. It moved from -20 to +10. It moved 10 units, right? Twice the movement. In fact, if I move this constantly, you can see that the red line seems to be moving at exactly twice the rate of x. It's moving at twice the speed. So that dy dx is talking about how fast is y moving compared to how fast is x moving, or how fast is y changing compared to how fast x is changing. Ends up, that's just a measure of the slope. It's moving twice as fast, moving along that line of 2x. All right. So let's actually explore a situation. What if instead of dy dx equaling just straight up 2, what if dy dx was something like 2x? Then that rate of change, how fast y is changing, depends on what x is at that time. If I do the same thought with the apples and the oranges, let's say we've got 1, 2, 3, 4 oranges in there right now, and it doesn't matter how many apples. Let's just say there's 1 apple. But the way this works is it says how fast y is changing will be 2 times whatever x is at that moment in time. So if x is 4, and X says, I'm going to put one more orange in there. Y is going to look at that and say, well, there's 4 in there already. 2 times 4 is 8. I'm going to put in 8 apples. 1, 2, 3, 4, 5, 6, 7, 8, right? Tons of apples. All right, now there's 5 oranges in there. And X says, I'm going to add one more orange. And Y looks at it and says, well, there's 5 oranges in there. You're adding one more. 2 times 5, that's 10. I'm going to add 10 apples this time. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So that's how that works. You can see this graphically as well. This is more of like an x squared feature. If I graph y equals x squared, this is one of those ones we did in the other lesson, the other video. We found that dy dx was indeed 2x. And we found that on this graph, the slope changes, right? At 0, the slope was 0. At 1, the slope is 2 times 1, which is 2. At 2, the slope is 2 times 2, which is 4. At 3, guess what the slope is? 2 times 3, which is 6. So it's to say the slope gets steeper and steeper and steeper. That same thought with the graph I showed. I'm going to show that again. Here's a graph of an x squared function. It's shifted over a bit, but it's still x squared, so it's still going to have that same thought. Watch what happens to that red y line as I move x constantly. It's moving, it's moving, it's moving, it's moving, it's moving, and then it goes faster and faster. Did you see how that went? The bigger x gets, the faster y moves. Same type of thought. So when I'm trying to find the slope, I want to find the slope at a particular point. This is actually going to lead us to the last meaning of dy dx. Okay, so here I've got 2 graphs, y equals 2x, which again we know dy dx is just going to be 2 because the slope of 2x is a slope of 2 everywhere. It doesn't matter where you go. And this one, y equals x squared, we worked out in the other video again that dy dx in this case would be 2x. So the slope depends on what the value of x at that time. But here we need to talk about a little something. Finding slope, right? One way to find slope with a line is finding the change in y over the change of x, right? Those subtract the y's on top, subtract the x's on top, on bottom, sorry. Another way we can see this here, I'm going to write y2 minus y1 over x2 minus x1. That's slope. And it's finding the slope between 2 points. Notation for this is delta y over delta x. That delta, that's a Greek letter delta, it stands for change in. So that's measuring the change in y, how much y is changing, and the change in x. And that gives us a slope of a line, right? Now, we talked about this, of course, before. If I wanted to find the slope on a curve at that one particular point, that slope formula causes me problems, right? So there's my delta y, there's my delta x, because then that slope's not going to be quite right. I'm actually a little bit more like this, right? And so when we talked earlier, we talked about using a limit function. We said, hey, if I want to find the limit at the slope at that one particular point, we would say, you know what, no, I can't use 2 points. I got to have these 2 points get closer and closer and closer to being the same point. We've talked about this a bit. And we found out that the slope at that one particular point is that limit function as h goes towards 0 of f of, let's call this point a plus h minus f of a all over h. We've talked about that. We know that's equal to slope, right? But then this dy dx, it actually comes from that idea, because if I wanted to find the slope at that one particular point, right here, if I wanted to find the slope right there, these 2 points are too far apart. That delta y and that delta x, they're too big, they're too far apart, it's not going to be accurate. We want to bring this point closer and closer to there. In other words, if I want a more accurate slope, I don't want this triangle to be so big. Instead of having that big triangle, like, that slope's too big, I want to zoom way in and I want a triangle that's as small as possible, right? I just want these points to be so close together, they're practically the same point. So over here, when I'm trying to find that slope with delta y, that change in y, and that delta x, that change in x, that's just way too much of a change. I want to be as precise as possible. I want my change in y to be super small, infinitesimally small. Infinitesimal. That's the idea of infinity, but backwards. Infinity is something that goes on bigger and bigger forever. Infinitesimal is something that's getting closer and closer and closer and closer to zero. Infinitesimal, that's what infinitesimal. So I want something infinitesimally small, something crazy close to zero. That's how small I want this. And there is a notation for something infinitesimally small. Instead of delta y, it's dy. I also want this to be infinitesimally small. So that's dx. So when I do that delta y over delta x, to get an accurate slope at a particular point, instead of doing delta y over delta x, those deltas are too big. We're going to use an infinitesimally small change in y. We're going to use a dy over dx. That's my slope at that particular point. But you'll notice, slope, same idea, just different notation. So literally when the people ask like, what does that dy stand for and that dx stand for? That dy stands for an infinitesimally small change in y. And that dx is an infinitesimally small change in x, which is slope, change in y over change of x. We're just going infinitesimally small, so we find the slope at a particular point. All right. I hope that helped you understand what that dy dx is there for, why we care about it, why it's a thing, and maybe you have a little better understanding of the meaning of it. See you later.